Hello, am I audible?
Yes,
Okay, and my screen is also visible, right?
yes.
Okay, so we'll start the session in a bit. We'll like wait for like 2-3 minutes and like wait for people to join, and then we'll start. Okay, so let's begin. Good evening, everyone. I am Nidhi. I am a PhD student at ISER Mohali, and I welcome you all to the second problem-solving session of of NPTEL course Graph Theory. So, last time we talked about Eulerian trail, Hamiltonian cycles, and paths and trails, etc. So today we'll continue talking about Eulerian trail, Hamiltonian cycles, and then we'll also talk about diameter of the graph and bipartite graphs. So first of all, what is so just to quickly recall the definition, Eulerian trail is a trail which is covering all edges of graph, and it should have same initial and final point. And an Eulerian graph will be a graph having a Eulerian trail, and for Eulerian graphs we have a nice necessary and sufficient condition, that is we have a good criteria to check whether a given graph is Eulerian or not. A graph is Eulerian if and only if all vertices have even degree. So this is the condition for graph to be Eulerian. Next, we'll talk about Hamiltonian cycle. So Hamiltonian cycle is a cycle which cover all the vertices of the graphs. And unlike Eulerian graphs, we don't have a nice necessary and sufficient condition for showing whether the graph is Hamiltonian or not, but we have some necessary separately and some sufficient conditions. For example, we have Dirac's theorem, which says that if degree of each vertex is greater than equal to n by 2, then graph G has to be Hamiltonian. And so this is only a we can see that this is only a sufficient condition, that is it is not a necessary condition. By saying that it is not a necessary condition, we mean that if a given graph is Hamiltonian, this need not be true that degree of each vertex should be greater than equal to n by 2. We can simply take any cycle graph, they are Hamiltonian trivially, and they won't satisfy this condition. So if we have to check whether a given graph is Hamiltonian or not, we have some nice condition. First condition is this, that if a graph is Hamiltonian and if we are removing k vertices from that graph, then the number of connected components of g minus v1 till vk should be at most k. There should So if we are removing k vertices from the graph, then the leftover graph should have at most k component. And then there's another theorem, that if uv is not an edge of a graph, and if degree of u plus degree of v is greater than equal to n, then g will be Hamiltonian if and only if g plus uv is Hamiltonian. And the last one is that if the G is Hamiltonian, if and only if CL, closure of graph, is Hamiltonian. By closure of graph means we keep on adding these edges UV with if we have any two vertices which is satisfying this condition that du plus dv is greater than equal to n, then we add that edge UV. So, is there any confusion between for definitions of Eulerian trail and Hamiltonian cycle? Is everyone clear about Eulerian trail? Is everyone clear about Eulerian trail and Hamiltonian cycle? Their definitions? Okay.
On these necessary conditions, though it is
Yes.
clear, but we will solve some problems in this.
Yes, yes. So last time also we solved some problems. Yeah, yeah. So basically, the first one is the mostly used. So I think there was some like we have solved some problem using this condition, right? That if we are removing these k vertices, and we'll see. Okay. Uh, Then the third thing is a bipartite graph. So what is a bipartite graph? Bipartite graph is a graph whose vertices set can be divided into two sets A and B, and these two sets A and B have a special property, that is within A there is no edge and within B there is no edge. So the only possibility for edges is to have any edge should have one vertex in A and other vertex in B. So there are no edges allowed within A and within B, and such kind of set is also called an independent set. So what is an independent set? A subset of vertices such that there is no edge between them. So we can see so the bipartitions of the bipartite graph A and B are independent set. And we also have a nice condition for nice, necessary and sufficient condition. If we want to know whether a graph is bipartite or not, then it is G is bipartite if and only if it has no odd cycles. So this is a necessary and sufficient condition. So if you have to show some graph is not bipartite, it is sufficient to find an odd cycle. If you can find an odd cycle in a graph, then you can say that your graph is not a bipartite graph. And if there is no odd cycle, then you can then that graph has to be bipartite. So these are some examples. So first one is a general example, is like we have vertices set which are partitioned into subsets, and you can see any edge has one vertex, any one vertex is there and other is there. There are no edges within A or within B. Then as nice and sufficient condition is that we want no odd cycle. So an even cycle is a bipartite graph because it has just one cycle and it is of even length. And then we had a notion of complete graph. Similarly, we also have a notion of complete bipartite graph. So if it is KMN, we put M vertices in our bipartition A and N vertices in bipartition B, and we connect all the vertices of A with all the vertices, we connect any vertex of A with all the vertices of B, and we do it for all the vertices, and the resultant graph is the complete bipartite graph. Okay. So is definition of bipartite graph is also clear?
Yes.
Okay. So now, yes, is there any question? Okay. So now we'll look at some questions. So let G be a tree. So if G is a tree, is G Eulerian? Can we say can we say can a tree be Eulerian? So what do you think?
Yes, ma'am. If it is even, then we can say if that all the degree is even.
Yeah. Oh, if all the degree is even. But what is the condition for Eulerian? Uh, you should
All the degree should be even.
all the degree should, but what is the definition of Eulerian graph? What do you need to find? You need to find a trail.
All edges are covered.
All edges
Yeah,
are covered
once.
and it should begin and end with the same point, right?
Yes.
So can a tree be Eulerian then? can tree have all the vertices of even degree?
No.
Because tree has no cycles, right? Since tree has no cycles, we cannot find a closed trail. So tree can never be Eulerian. Is this clear why tree can never be Eulerian?
Yes.
Yes. Okay. What about bipartite? Can is tree bipartite?
Yes,
Yes. Okay.
Yes. Yes.
Why trees are bipartite?
because tree doesn't have any cycle.
Yes, tree doesn't have any cycle, and we have necessary and sufficient conditions says for bipartite it should have no odd cycles, but tree have no cycles, therefore it cannot be bipartite either. And what about Hamiltonian?
Tree is not Hamiltonian
Why?
because we have to in Hamiltonian we have to use vertex only once.
Yes.
So if we come down with
Hmm.
one vertex, so then to going to another branch we have to use that same node, which is not possible.
Yes, and there's one simple reason also, like, right. So you can if graph is Hamiltonian, if and only if it has an Hamiltonian cycle, but trees can't have any cycles, right? Therefore, it cannot be Hamiltonian either. So basically, since tree cannot have any cycles, therefore cannot be Eulerian. They can't be bipartite and they can't be Hamiltonian. Is this clear? the reason
Yes.
the reason for all three is same, that trees have no cycles. No. So now the next question is, we call a graph G semi Eulerian. So this is G is called semi Eulerian if it is not Eulerian, but it has a non closed trail covering all edges of G. Okay, so basically a semi Eulerian graph is a graph in which we can find a trail which is covering in which we can find a trail which is covering all edges of G, but that trail is not closed, that we don't want that it starts and end at the same vertex, so it is a trail. So basically it no edges should be repeated, plus we don't want it to be a closed trail either. So now the question is that if G is semi-Eulerian, we have to show that G has exactly two odd vertices. Okay. So for G to be Eulerian, we know that all vertices have to be even. But if we are defining semi-Eulerian graph to be a graph which is not Eulerian, but we can find a non-closed trail covering all edges of G. Then G should have exactly two odd vertices. So is the question clear? So anyone has any ideas how to proceed with this question?
Ma'am, first we will assume that we have found a trail from V1 to Vn, and supposing if Vn has an extra, the degree of Vn is 1, but if we say that the degree of Vn is one more, then we will always find another vertex. That is, this means that our trail is not completed, so we have to extend it to Vn plus 1 vertex. And when it is extended to Vn plus 1, the Vn plus 1 will only have one vertex only.
Hmm. Okay. So you are saying that, but it need not be true, right? That Vn has just like if we are finding an Eulerian trail which is starting from V1 and which is ending at Vn. It need so in a trail we are not allowed to repeat an edge, but we can always repeat an vertex. So from if we are able to find a trail from V1 to Vn, that doesn't mean that degree of V1 and degree of Vn has to be 1, right? Because in a trail we are not supposed to repeat the edges, but we can repeat the vertices. So your argument, you are on right track, but your argument is little incomplete. Do you understand what right?
Basically, we cannot assume that the degree is one,
Yes,
so the
yes,
degree needs to be generalized.
yes, yes, yes. So
So we can.
yes, so he started on
So
right note. So if G is semi Eulerian, that means G has a non closed trail covering all edges of G. Suppose that trail has endpoints U and V. So now since G is semi-Eulerian, basically we have a graph G and we can cover basically, and there need, so we have this U and V, and we are covering all the edges of the graph basically. So we have some trail in which vertices are allowed to be repeat, but we edges can't be repeated. So we have some trail like this. We have some trail like this which is starting from U to V, and it has all the edges. Now tell me, what can we say about the graph G plus? So now since now uh, now what can we say about the graph G plus UV?
Then it is cycle, ma'am.
So the G is this graph. Now I am saying G is this graph and I am adding one more edge to this graph. Say I am from this G, I am constructing new graph H which has one more edge.
Then it is Eulerian cycle.
Okay. Yeah. So this was G and this. Then it is an Eulerian cycle. Yes. So basically you are saying that graph H is Eulerian, right? So is right. So if so graph H is Eulerian, right? That is G plus UV is Eulerian. Now if G plus UV is Eulerian, what what can we say about the degree of vertices of H? Now if we can, now I'm saying that G plus UV is Eulerian. G plus UV is Eulerian. So this is
So
an
H is degree is even then.
yes, good.
Even.
So all the vertices in G plus UV has even degree. Now, now using this, we have to now we know the degree of each vertex in graph H. Now using that, we have to find the vertices of degree find the degree of the vertices in graph G. So suppose I pick a vertex W Suppose I pick a vertex W in H, but W is not equal to U or V. So what can I say about degree of W? So we know that degree of W in H is even. So what can we say about degree of W in G?
It is also even,
Why?
because inside, if you see inside that except U and V, every node is connected with what you say, two branches. So
There can be
two
limited.
edges.
Yes, because in the new graph we have only added one edge. So degree of W is not affected at all. Degree of W in G is same as degree of W in H, right? So this is fine. Degree of W in G. But what is degree of U in H? Degree of U. What is degree of U in H?
It is two. It is even.
Even. Even. And what can we say about degree of U in G?
It is odd.
Because it is degree of U in H minus 1, and therefore odd. And similarly, degree of V in G, because in the new graph we have only add one edge. So only this degree is not only the degree corresponding to this edge is not counted in our original graph. Therefore we can say that degree of U, this is U, degree of U in G will be degree of U in H minus 1, and similarly degree of H V minus 1 odd. So how many odd vertices we get?
Two.
2. So is this question clear to everyone? Is this question clear
Yes.
to everyone?
Yes. Yes.
Okay. Next question. So so we have that. Okay, sorry. So we have that KMN is a complete bipartite graph, and I defined what is a complete bipartite graph. So first question says that if KMN is Hamiltonian, then M plus N should be odd or even. What do you think? So we are given that this KMN is a bipartite graph, and we are also given that this is Hamiltonian. So what should be the condition on M plus N? Any guesses? Okay. So, first of all, if KMN is Hamiltonian, what do we mean by that?
It is odd, ma'am. It is odd.
Okay. Why? Why?
I have taken one example of k m is equal to 2 and n equal to 1.
Sorry, what is your example?
K equal to 2, m is equal to 2 and n equal to 1.
So you are saying K21. Yes. Okay. So K21 is this, right? So K21
Yes.
is this. So is this Hamiltonian?
It is not a cycle, but
Huh, but for it to be Hamiltonian, we need but for it to be Hamiltonian, we need a cycle which is covering all vertices of graph. So, but this does not have a cycle, so this cannot be Hamiltonian, right? Bec- if do you understand why it is not Hamiltonian? What is the definition of Hamiltonian?
yes,
Hamiltonian
yes,
graph.
yes.
Yes.
Even is the answer. Sorry, it is the opposite. If you take K22, then the cycle will come.
Yes. K to 2, then cycle will come. Okay. But it is working for that example. So if you are saying K to 2, then K to 2 is this basically. And you are saying this is Hamiltonian. Yes, it is Hamiltonian, right? If this is K2, your Hamiltonian cycle is basically ACDBA. So it is Hamiltonian. So it is working for working for K to 2. But why it should, but if we are saying that M plus N should be even, we can't just show it through one example. We'll have to give an argument, right? So why do you think it should be even? So first of all, so KMN is a bipartite graph, and if KMN is Hamiltonian, that means if KMN is Hamiltonian, that means there exists a Hamiltonian cycle. Hamiltonian cycle, that is, we have a cycle which is covering all the vertices of this Hamiltonian graph. So how many vertices this graph has? M plus N. So we have a cycle covering all the vertices of graph, and suppose I am ordering them in a manner in the way I am getting the cycle. So what is the length of this cycle? What is the length of this cycle?
M plus n.
M plus N. Right. Good. Is there exists a Hamiltonian cycle of length M plus N. And now this is a bipartite graph, right? So can a bipartite graph have an odd cycle?
No.
No. So if this is a Hamiltonian cycle which is contained in a bipartite graph, therefore this cycle is of even length, and therefore M plus N should be even. So is everyone convinced why M plus N should be even?
Yes.
Okay. Now second question is K24 Hamiltonian? So first let me draw K24 and then you look at this picture and let me know if you think it is Hamiltonian or not. So if it is K24, that means first set has 2 vertices, second set has 4 vertices, and every so we will connect this vertex with every vertex in B. This is A, this is B. So if it is Hamiltonian, we should be able to find a cycle which is covering all the vertices of this graph. So what do you think? Is K24 Hamiltonian?
No,
Why?
because when we will go according to the bipartite graph definition, we have to again switch to the A set, and A set doesn't have any enough vertices to match it up.
Yes, good. Yes, you're right. So basically, what is he saying? Suppose, suppose it has an Hamiltonian cycle. We'll prove it by contradiction. It has a Hamiltonian cycle. That means we can find a cycle covering all the vertices, and there are 6 vertices. So we can find a cycle covering all the vertices of this graph. Now, suppose W1 is belonging to A. So what can we say about W2? Where should W2 belong? A or B?
B.
B. What about W3?
A.
A. So basically we see that odd, basically W1, W3, W5 should belong to A. And in a cycle, we are not allowed to repeat the vertices. But we see that A has only 2 vertices. Therefore, we cannot have a Hamiltonian cycle in this graph. A has only 2 vertices. So, not possible. So, because see, even if you want to try to make an Hamiltonian cycle, what we'll do? We'll start with say V1, then we'll go here, then we'll go here, then we'll go here. But now we have no other vertex in A to complete our cycle. So this is the therefore, and we also have reason also. So did everyone understand why K24 is not Hamiltonian?
Yes.
Now, using this example, can you tell me, can you put any conditions on conditions on M or N to ensure that it is Hamiltonian?
Both even, ma'am. Multiple of
Both
2.
should be equal.
What values of M, N,
M is equal to
yeah,
N is equal to both even.
M, N. Okay, so there is one answer which says M equal to N, and there is second answer which is saying that M equal to N, and M and N should be even. And like for we are assuming M, N greater than 1, M N greater than 1, because if M N and 1, it is just one line and it can not be Hamiltonian. Okay, so okay, oh sorry, so first person said M equal to N. He didn't say that M and it should be even. So why do you think that only saying M equal to N is enough? Let's okay, let's look at an example. Let's look at K33.
We will be able to find uh, the cycles. I don't know anything about the generalization of it, but
Yes.
the I think it's about observation here.
Okay. Yeah. So basically, yes, it is a complete bipartite graph. So it has all the edges. So if it is K33, suppose my vertices are V1, V2, V3, V4, V5, V6. So basically, if I want to find a Hamiltonian cycle, so we have this. So now, so see, if we if we start with V1, we can go to V2, then we can go to V3, then we can go to V4, then we go to V5, V6, and then we can go to V1. So if M and N are odd also, then also we are getting a Hamiltonian cycle in K33. So this two should be this should two M and N should be even, need not be necessary, because in case of odd also we are getting a cycle. So how are we getting a cycle basically? How can we ensure? So I'm saying that first answer is correct, that KMN is Hamiltonian if and only if M and we are assuming that Mn is greater than 1. If and only if M is equal to N. How? So I'll call my first bipartition. So if it is M equal to N, I'll take my first bipartition as V1 Vn, second partition as W1 Wn, and I can consider the cycle V1 W1, V2 W2, Vn Wn, and V1. So this is the required Hamiltonian cycle. And we can always find a edge between V1 and W1 and V2 and W2 because it is a complete bipartite graph. So V1 is connected to every vertex in W. So we see that if M is equal to N, then KMN is Hamiltonian, and if M is greater than N or less than N, the similar argument as B, that we ran out of vertices, will work. And therefore we see that if Kmn is Hamiltonian, then M should be equal to N. Is this argument clear?
Yes.
So if everyone convinced that a complete bipartite graph can be Hamiltonian if and only if M is equal to N. Okay. We'll go to the next question then. Now question 4 is, let G be a bipartite graph. If there exists a path of odd length between U and V, show that any path between U and V is of odd length. So proof. So first of all, we know that G is bipartite if and only if G has no odd cycles. Now the question 4 is saying, suppose U and V are two vertices, and suppose there is a path between U and V and the length is odd. I call this path P1. And suppose there is another path P2. Suppose there is another path P2. I have to show that this path P2 should have odd length. So now why is this true? So U and V are two vertices of a bipartite graph G, and they have a path of odd length, say P1. Now the question says that any other path between U and V should be of odd length also. Why that is true? So this is P1, it has of odd length. Now we have to show P2 has odd length. Why do you think it is true? Can P2 has even length? So UV is a path, say U is going from U1, UK, V. This is my path P1. so the question is, so you show any path which is disjoint from P1. P1 is odd length. Sorry. So the question is basically we have a path P1 of odd length, and there is a disjoint. There is another disjoint path of P2 of odd length. Sorry, we have to show that there's a disjoint path P2 between U and V. We have to show that P2 has odd length. So there is another path, say W1, WM, V. So can P2 be of even length? What will happen if P2 is of even length? So G is bipartite if and only if G has no odd cycles. There exists path P1 of odd length, then show any path disjoint prof P1 between U and V is of odd length. Okay. So any guesses why P2 should have odd length?
Ma'am, because if P1 has odd length,
Yes.
then if, every time if we have to find a new path, we have to add two edges, right? So odd plus two would be maybe.
So okay. So let's say I am saying if it is a odd length path, say I have a odd length path of three vertices. Suppose this is U, this is V, and I have V1, V2. This is an odd length path. And now suppose there is some other path, V3, V4, some other path which does not have V1 and V2, or U and V, which does not have V1 and V2, VK, 2V. So this is odd length, right? So now you see if this is path P1 and this is path P2. So basically if I go from U to V and then back to V to U, I am getting a cycle, right? If I am going from U to V, so basically this was one path, this was one path, and this was other path between U and V. So two disjoint paths between U and V are giving me a cycle. This is of odd length, and since it is a bipartite graph, this cycle should be of this cycle should be of even length. So what should be the length of this path? So basically I am saying if there are two paths from U, if there are two paths from this P1 and P2, if I go from U, U1, UKV, and then I go in the reverse P2, that is WM till W1U, I am getting a cycle. And we know that this cycle should be of even length. So if this was of if this path P2, if P2 is of even length, what is the length of this cycle? Odd or even?
Odd.
Odd.
Odd, odd.
So the cycle has odd length, which is not possible, right?
Bipartite graph.
Yes.
Yes.
Sorry.
Madam, if we take P1 as a even, then again then P2 is also even, na?
Yes,
In the similar.
that is the second part of the question. Yes.
So
Hmm.
yes, yes.
So of even length, then cycle C1 is of odd length, which is not possible. And the second part of the question was, if I replace my if I replace the above sentence in the above sentence odd by even, what happens? If my original path was given to be of even length, what can I say about the second path? It
Again,
should
it is even.
it should be the
Even.
even length, because if we take it to be odd, then we are getting a odd cycle, which is not possible. So is this question fine?
Yes, yes.
Okay. Now next question is this. So is everyone aware about QN, hypercubes? Is everyone aware what QN look like? What do we mean by the graphs QN?
Yes, cuboid, ma'am.
No, as in QN is basically vertices are tuples A1, AN, where AI is 0 or 1, and edges edges are A1, AN, B1, BN, if they differ in exactly one entry. So everyone understand what is Qn? Vertices are basically n tuples of number, n tuples of 0 or 1. And we have an edge between those two tuple if they are differing in exactly one entry. So here I have drawn Q2. So if it is Q2, what are the possibilities? Either it can be 0 0, 0 1, 1 0, or 1 1. And there is an edge only if they are differing in one entry. So 0 0 and 1 0. They, only in the first entry they are different. Therefore, there is an edge between them. But there is no edge between 0 0 and 1 1 because they are differing in two entries. So is everyone clear about the definition of Qn?
Yes.
Yes.
So if you're clear, so tell me, if we have general n, how many vertices will have? What is the count? What is the number of vertices of Qn?
And
Not n. See, if
2
it
to the
is
power
Q2,
n.
if this is Q2, we are getting four vertices.
2 to the power n.
Two.
two to the power n.
Yes, because we have A1, AN, and each entry has two options, 0 or 1. So 2 cross 2 cross n times, which is 2 to the power n. So now the question is Q2 bipartite? What do you think? Is it bipartite?
Yes.
Why? So if it is bipartite, then you have to give me set A and set B.
Set A will
So
be 0,
0 0 and 1 1 is set A,
Okay. Yes.
and B is 1 0 0 1.
1 0 0 1. So is he correct? So there's an entry, there's a edge between here, there's an edge here, and there's an edge here, and there's. So why there is no edge between 1 0 and 0 1?
because they differentiate at two places.
Yes. First entry is also different, second is all. So Q2 is bipartite. What do you think about Q3? Is Q3 bipartite? If it is bipartite, you will have to give me appropriate bipartitions. Okay, first of all, if we have 0, 0, 0, without looking at the graph, can you tell me, can you tell me what all edges will be adjacent to, what all vertices will be adjacent to 0, 0? This 0, 0, 0. If the graph was not there.
001.
0, 0, because we are only allowed to change one entry. Yes, 0, 0, 1,
010.
0, 1, 0, and
100.
1, 0, 0. So see, this has three zeros, but all others have two zeros. So now can you think why this graph is a bipartite and give me appropriate bipartitions?
Ma'am, it is bipartite, and I will give you set A and B.
Okay, yes, give me.
Set A, start, ma'am.
Yes, yes.
010.
0, 1, 0,
Then it is 100.
1, 0, 0. Okay,
Then it is triple one.
triple 1.
Then
Okay,
001.
0, 0, 1. Okay, and set B is basically the remaining one you're saying.
Yes, ma'am.
So is he correct? What do you think? So he has given me these four options. So these sets. I'll write the other ones also. Uh, and yes. So he has given me these as bipartitions. So do you think he is correct? So first tell me, can there be a edge? So can there be a edge between 0, 1, 0 and 1, 0, 0? So in how many entries they are differing?
Two.
They are differing in two entries, so this is they cannot have an edge. And similarly, we see all these cannot have an edge between them, because 1, 0, 0 and 1, 1, 1, this is also differing in two entries. 1, 1, 1 and 0, 0, 1 is differing in two entries. And if you notice, if you notice vertices in A all have even numbers of zeros, and vertices in B all has odd number of zeros. Why do you think that is the case? So we'll see. So 0, 1, 0. So first of all, what all vertices will 0, 1, 0 be connected to? We are just allowed to change one entry. So it will be connected to 1, 1, 0 if we change the first entry. If we change the second entry, it will be uh, triple 0. And if we change the third entry, it will be 0, 1, 1. And similarly 1, 0, 1, 1, 1, 0, 1, 1, 0 and triple 0. So given any number, without looking at the graph also, you can tell me what all edges will be there. So we see that this is a bipartite graph because there is no edge between this. So now triple one is connected to 1, 1, 0, 0, 1, 1 and 1, 0. And 001 is connected to 000, 011 and 0101. So is everyone convinced why Q3 is bipartite? Because we are able to find A and B. So Anupam, you find A and B. So how did you find A and B? What were you thinking? Like how were you able to find A and B?
Ma'am, as you said, only one digit to change, na ma'am.
Yes,
So
yes.
if you see the adjacent,
Hmm, hmm, hmm.
so whenever there is a change of only one, that is the connection.
Yes, yes,
So that is the basic idea.
yes. That is the basic idea. So basically, now if I was talking about Q4, now if I was talking about Q4, it will have 2 raised to the power 6. 80. It is very, sorry, 2 raised to the power 4. It will have 60, 2 to the 4, 16 vertices. So it is very difficult to make a graph. But still I am saying that we can conclude whether it is bipartite or not. So in the first, in all this we see that, or if we have odd number of zero, so partition A, sorry, partition A in this has even number of zeros and partition B has odd number of zeros. So basically here in this also, odd number of zeros are in partition A and uh, even number of zeros are in partition A and odd number of zeros are in partition B. So suppose I have this entry 0, 1, 0, 0. So how many zeros does this, how many, it has 3 zeros. It has 3 zeros and it will be connected to what all vertices? It will be connected to 4 vertices. So can you give me the vertices which it will be connected to?
One,
1, 1, 1, 0, 0.
100,
Yes.
then 0110,
Yes. So he first
then
changed the first entry, then he changed the third entry.
then again, yes ma'am, same, then next 010, last one.
And the second one, we can also change the third entry.
Yes.
Or second entry. So now here also see, this has odd number of zeros, but the vertices that it is adjacent to has even number of zeros. So I claim is Q4 is also bipartite and the bipartitions will be basically, we take first set which has odd number of zeros and second set which has even number of zeros. Because if we have suppose A1, A2, A3, A4 has odd zeros, so if A1, A2, A3, A4, if there are odd zeros and we are changing one entry, so either we are making 0, some 0, 1. So suppose it has k zeros and l ones, and we are allowed to change, and we are only allowed to change one entry. So if it has k zeros and l ones, suppose if I am changing a 0 to 1, so So the new one, the new and the adjacent vertex, suppose a1, it is adjacent to b1, b2, b3, b4, and if I'm changing one of the zeros, so how many zeros it has? If I'm making a 0 1, then that means it has k minus 1 zeros, because I'm replacing 0 with 1, so I have one less 0. And similarly I'm adding 1 1, so I have l plus 1 ones. So if earlier I have k zeros, in the new one I will have k minus 1. So either I can replace 0 by 1, or the second thing I can do is I can replace 1 by 0. If I replace 1 by 0, I have added one more 0. Therefore, I will have k plus 1 zeros and l minus 1 ones. So we see that if the initial vertex has k0, the vertex that it has adjacent to will either have k minus 1 zeros or k plus 1 zeros. Therefore, if it has odd zeros, then the vertex that it is adjacent to will have even number of zeros. Therefore, hence in Q2 and Q4, in Qn we can have vertices will have A union B. A will be have vertices which have odd number of zeros, and B will have vertices which has even number of zeros. So and we, from this argument we see that A cannot have any edge within them and B cannot have any edge within them. So we are able to find two independent sets, and they are disjoint also. Therefore we see that Qn will be bipartite. So okay, did everyone understand why it is a bipartite?
Yes.
Any doubts in this? Okay. Okay. So now these were questions on this. Now other things that were introduced this week were graph isomorphism and diameter. So we say two graphs G and G prime are isomorphic. Okay. Is there a question? Okay. We say two graphs are isomorphic if and only if we can find a function between vertices of G and vertices of G prime, which is a bijective function, plus UV is an edge of G if and only if FU and FV is an edge of G prime. So this is graph isomorphism, and we can see that if two graphs are isomorphic, they share many similar properties. They will have same number of vertices, they will have same number of edges, and they will have we can talk about their degrees also. So if U has degree m, then Fu will also have degree m. So this is graph isomorphism. Our first question is, isomorphic graphs have same degree sequence. Is it true or false?
True.
True.
Yes, true. Because we see, so if we have a bijective function from V to W, and there's an edge between, there's an it's a bijective, and there's a so if we so basically VG and VG prime, we have, so if suppose this is the function f and V is going to W, then if number of vertices that if V is adjacent to U1 UK, then W will be adjacent to FU1, FUK. So we see that degree of V is same as degree of FV, and therefore they have same degree sequence. What about the second question? Graph with same degree sequence are isomorphic.
False.
False.
So if you're saying false, do you have a counter example?
Ma'am, don't have the counterexample at the time, but the positions also matter about this vertices position
Yes,
matters
yes, the
because
paths that it has basically. There, the length of paths also matter, and how they are placed also matter. You're right. So, so does anybody else have an counter example? Okay, so I'll give it. So if we just look at this graph, so are these two graphs? First of all, what is the degree sequence of first graph? So this has degree 1, this has degree 1, this has degree 1, this has degree 2, this has degree 2, and this has degree 3. So the degree sequence is basically 3, 2, 2, 1, 1. And is this degree sequence same for this one also?
yes,
Yes. But are they isomorphic?
no.
Why? Now you'll have to give a reason why they are not isomorphic. So this is
Because if we look at D here, it has degree sequence 3, but the adjacent to D is C. We have it has degree sequence 2, but in the second graph, the degree sequence of V3 is 3. That is fine, but V2 has degree sequence adjacent to it. We have degree sequence V2, which has degree 1.
but okay. So you are saying V3 has degree 3 and V2 has degree 1, right?
Hmm.
But here also we have a degree 3 and degree 1 vertex adjacent.
But here, if we
Acha,
look at C and D, both have degree 2,
yes,
and adjacent to it, it has 1 and 2.
yes, that is fine. Here
That is
degree here we have degree 3 vertex is adjacent to 2 degree 1 vertex. But here degree 3 vertex is adjacent to only 1 degree 1 degree 1 vertex. Therefore, they cannot be isomorphic.
Ma'am, what is the degree sequence? How to write this second graph?
What? Yes, so basically you'll say that uh,
No, just like you have written first ka degree sequence, please
hmm,
write for second also.
degree sequence is basically you write it in the descending order or ascending order.
So then, by writing the degree sequence, you cannot make out na whether the graph is isomorphic or not.
So this is the question that graph with same degree sequence are isomorphic. So we are saying false. So these two graphs have same degree sequence, but they are not isomorphic. And the reason is basically, and the reason is basically in if this is graph G and this is graph G prime. Uh, by degree sequence we mean this. So G both G and G prime both G and G prime have one vertex of degree 3. In G, degree 3 vertex is adjacent to only one degree 1 vertex, but in G prime, degree 3 vertex is adjacent to two vertices of degree 1, which is not possible if they are isomorphic. So, if there was some isomorphism, since both have only one vertex of degree 3, in that isomorphism, this degree 3 vertex D should go to V3. But we see the vertices which are adjacent to D are C, E, F, and only one vertex has degree 1. Whereas in G prime, we have a degree 3 vertex which is adjacent to two vertices of degree 1. Therefore, they cannot be isomorphic. Because if they were isomorphic, the adjacent vertices should also, the adjacent vertices, if it was an isomorphism, and if it was an isomorphism and D was going to V3, the degree of adjacent vertices of D should match with the degree of adjacent vertices of V3. But in this case, it is not matching. Therefore, it is not an isomorphism. And if any, and there is only one vertex of degree 3, so D has to go to V3. D cannot go to any other vertex if there was an isomorphism. So do you understand why G and G prime are not isomorphic?
Yes.
So first we are saying, first see, we are proving it by contradiction. Basically, if it was an isomorphism, then a degree 3 vertex should go to a degree 3 vertex. There is only one degree 3 vertex in G and one degree vertex in G prime. So D can only go to V3. But now, and all the adjacent vertices to D and adjacent vertices to V3 have different degrees. Therefore, they cannot be isomorphic. So we
Ma'am, is there any other method to find out isomorphism?
we basically, you have to, no, they are not isomorphic. So you have to give any reason. So one of the reason that he gave was this. Other reason can be, see, basically you have to find some condition which is not holding. Other reason can be, so this, you have, this graph has only degree 2 vertices C and E, and this graph is also have only 2 degree vertices V4 and V5. But these two are adjacent, these two are not adjacent. So this is also not possible. So other reason why they cannot be isomorphic is this. So there are two degree 2 vertices which are C and E. Here it is C and E. Here it is V4 and V5. So C should go to either V4 or V5, and E also should go to V4 or V5 in an isomorphism. But in this case, C and E are not adjacent, but V4 and V5 are adjacent. So another reason can be this. So basically, you have if you have to show it is not an isomorphism, you have to look at their degree closely and find some contradiction. And if there are paths and all, then you can, we'll look at more example and see why they are not, what are other reasons we can find. So is this clear why these two are not isomorphic?
Yes.
So okay, before going to question 7, so let's do more of these questions. So what about this? Are these two graphs isomorphic?
No.
Okay, so first question is, let's look at the degrees of each vertex. First list down the degree of each vertex. So this has degree 3, this has degree 2, this has degree 3. So so basically it has degree 3, this has degree 1, sorry 2. This has degree 2, this has degree 2, this has degree 3, and this has degree 3. So the degree sequence for the first one is 3, we have 4 vertices of degree 3 and 4 vertices of degree 2. And similarly, here we see this is degree 3, degree 3, degree 2, oh sorry, 3, 3, 2, 2, 2, 2. So here also we have, so they have same degree sequence. So this reason we cannot give. So now somebody said that they are not isomorphic. Why do you think they are not isomorphic?
because the di- vertex of degrees, which are uh, three in the inner rectangle, in the inner squares, uh, it is in opposite. So the again the positioning of it matters.
Sorry, can you repeat? What do you want? What are you
I'm
saying?
s- I'm saying that in the first one they are in the opposite directions, like they are in the like 2 to 3 and H to 3. Sorry, what it is? C to
C,
A, I think.
C to A, yeah.
Yes, and H to 3. They are in the opposite, so they are in diagonal way. And here we have 1 to 3 and 4 to 2.
Okay, but
So
see, yeah. So, but what diagonal? So this is just a drawing. So we know two isomorphic graphs can look very different also. So we can't say that they are
yes,
they are
but
so you
like in the if we give it in a reasoning way, we will say that 3 and 4 both are adjacent and both have degree 3. But here we don't have two, which is, but we don't have a vertex which is adjacent to C, which which is adjacent to C such that its degree vertex is 3.
okay, yeah, that reason you can give, that here we have a degree 3 vertex which is adjacent to 2 degree 3 vertices. But in this graph, we don't have any degree 3 vertex which is adjacent to 2 degree 3 vertices. Right? This is the reason you are giving, right?
Yes.
So they cannot be isomorphic. Yeah, that is true. Because that is right. If this is G, G prime, G has a degree 3 vertex which is adjacent to, sorry, G prime has a degree 3 vertex which is adjacent to 2 degree 3 vertices. But there is no such vertex in G. So they cannot be isomorphic. So is this reason clear to everyone why they can't be isomorphic?
Yes.
Okay. Uh, what about B? What do you think? Are they isomorphic?
No.
Why? So let's look at the degree sequence. So this is 2, 2, 2, 2, 2. And this is also 2, 2, 2, 2, 2. So you said it, they are not isomorphic. Why are you saying they are not isomorphic?
I think they are isomorphic.
So if you are saying they are isomorphic, then you have to give me the map. Like which vertex is going to which vertex. And if you are saying that they are not isomorphic, then you'll have to give me a specific reason why they are not isomorphic.
Mm, F equals
So see, this is a cycle.
to
We see that this is a cycle. Is the other one a cycle? If other one is a cycle, then we can say it is they are isomorphic. Do you think this is a cycle? So this is this is basically C5.
This is cycle, but that is not a cycle, ma'am.
Okay. Why it is
it
not a cycle?
is a cycle.
If it is a cycle, then you have already have a map. Then you can send one vertex to the. So see, so this one has a cycle of length 5, which is given by vertex 1, basically v1 v1 v2 v3 v4 v5 v1. So this is the cycle. So if the other one, if it is isomorphic to this, first of all this should be a cycle, so you have to give me a cycle of length 5.
A C E B D A.
A C E B D A.
A.
So A C E B D A, right? So this is
Yes.
also C5 then, right? Because there are 6 edges. So how many edges are there in this graph? There are only 5 edges. A C C E E B B D D A. So if I send V1 to A, V2 to C, V3 to E, V4 to B and V5 to D, then this is then my G is also isomorphic to C5, right?
Yes.
How can we check? Because it has only 5 edges, and V1 V1 V2 is an edge, and these are the only edges: V1 V2 V2 V3 V3 V4 V4 V5 and V5 V1. And here also these are the only possible edges: AC CE EB BD DA. So they are isomorphic. This is the map. So I'm calling. So is it clear why it is isomorphic?
Yes.
So is this the necessary and the sufficient condition that if we have the same number of the vertices and along with the same degree sequence, and moreover if both the graphs are forming a cycle, then definitely both the graphs are going to be isomorphic?
Yeah, if it is a cycle, then yes. Because,
Okay, and yeah,
but
yeah,
if there
please.
was any additional edge also here, then so for cycle it is fine. Because if it is a cycle, basically if you have two cycles, they will be isomorphic if and only if they are same length.
And what if we have some additional edges here, and the given graphs are not cycles then?
Then we can't say anything. Then we'll have to look at specifically. Then we have to look and specifically see if it is isomorphic. Then we'll have to try our other methods, like see the degrees where, and if we basically, if this is the map if this is the map and you can find a edge bit here which is not here, then this map is not an will not give an isomorphism. So basically you'll have to find, if there are more edges, you'll have to find other reasons like we did in previous questions. You'll have to explicitly look at the degree of each and find
Okay.
some coordinate. If it is not isomorphic, then you'll have to analyze the graph appropriately, like we have done for previous others, to find a contradiction, to find something.
Okay. And what about proving two graphs non-isomorphic?
So we have shown various graphs non-isomorphic, right? So the in this one we showed that they are non-isomorphic by looking at the vertices. So we were able to find a degree 3 vertex in this second graph G prime, which is adjacent to 2 degree 3 vertices. But in this graph there is no such degree 3 vertex which is adjacent to 2 degree 3 vertices. So these two cannot be isomorphic.
But then this is totally a hit and trial approach. So what about something which is more algorithmic?
So yeah, if they are non-isomorphic, then there is no algorithm like thing. You'll have to observe the graph and analyze. Either you'll have to say that it has some odd cycle, but like if it has some cycle of length k, but there is no cycle of length k in this graph.
Okay, thanks.
Yeah, there is no algorithm to show whether they are not isomorphic or not. You'll have to analyze the graph.
Okay, thanks.
Yeah. So now I'll return to this question. So this question is, if G and its complement G bar are isomorphic, show that G has 4k or 4k plus 1 vertices, where k is a natural number. So basically, question 7 is G and G complement. So everyone understand what is a G complement, right? And G and G complement are simple graphs. G and G G is a simple graph and G bar is its complement, and we are saying that G and G prime are isomorphic. To show G and G are, and suppose G is a graph on n vertices. Suppose G is a graph on n vertices, given we are given that G and its complement G and G bar are isomorphic, and we have to show that n is equal to 4k or 4k plus 1. So first tell me what is G complement. So how so G has n vertices. So how many if G has n vertices, how many vertices will G prime have? The
n.
G complement. Sorry,
Same,
number of
same,
vertices in G
same.
complement
It is
is
same.
same. Okay. And what are the, now we are given that yeah. So suppose G is a graph on n vertices and m edges. And m edges. So number of vertices in G bar is n. What can we say about number of vertices in G bar is n? What can we say about number of edges in G bar? If G is a graph on n vertices and
And
m edges, why
they
m?
will,
Why m?
because they are isomorphic.
Okay. Suppose we were not given that, like this is for this special case. In general, if we have, you are right, it is m in this specific situation. But I am asking if G is any graph on n vertices, and suppose right now we don't have any condition on G bar. What will be the number of edges in G bar?
And NC2 minus M.
NC2 minus m. So yeah. So does everyone agree why this is true? So his answer is correct. Now, does why did you say NC2M
Ma'am,
minus M?
because
Yeah.
G and G bar, if we make any graph
Hmm.
and then we make its complement, and in the third part, if we want to represent it together, then it will always come a complete graph that it will be a Kn. And Kn is a complete graph and it uses highest number of edges, which is NC2.
Yes, very good. So basically, how is G bar constructed? If if we have some edge missing in G, then so if UV is not an edge in G, then UV become an edge in G bar. So if we look at complete graph, we have total NC2 edges, and G is using M edges. So all the leftover edges will be in G bar. And how many leftover edges are there? NC2 minus M. NC2 minus M. Okay. So now uh yeah, now NC2M, yes. So now if G and G bar are isomorphic, how many edges will G bar have? If G has M edges and G and G bar are isomorphic, then how many edges will G bar have?
We have to equate both.
Yes,
Then
it will be equal to M. Somebody already pointed out, because if two graphs are isomorphic, they should have same number of edges. So we get that NC2, which is n into n minus 1 by 2, is equal to minus M is equal to M. So we get that M is equal to, we take it here, so it will be 2M, and then we divide, so it will be n into n minus 1 by 4. Now, and this M is an integer. So did we now get what we wanted? Did we get what we wanted?
Yes,
Okay, why?
because if n is odd, then n minus 1 is even. And if n minus 1 is even, it has to be a multiple of 4
4.
because it won't divide n.
Yes.
And we can use the same logic for n minus 1. If it
Yes.
is odd,
Yes.
then
Yes. So if n is odd, then that means 4 divides n minus 1. Or in other words, therefore 4 is equal n is equal to 4k plus 1. And if n is even, if n is even, 4 divides n, and therefore n is equal to 4k. Therefore we get what we wanted. So is this question clear to everybody?
Yes, so and what about the converse of this statement? Because just because both the graph as well its complement are having the same number of the edges, it does not mean that both the graphs are isomorphic. So we have just taken one single property of the two isomorphic graph, that both the number of the edges should be same, and then we reach to this conclusion.
Yes, yes.
However, if we have been given two graphs, say G and G prime, and if the number of the edges in both the graphs is either a multiple of 4 or a multiple of 4 plus 1, then is it necessary that both the graphs are going to be isomorphic?
Okay. Yes, so you are right. So basically, his question is, so we have shown that if we are given that G and G bar are isomorphic, then we have conclude that n should be either a multiple of 4 or 4k plus 1. But is the converse true? That is, if n is equal to, suppose, say 4k or 4k plus 1, can we say, and they have, and G and G bar has same number of edges, can we say that they are isomorphic? Okay, good question. So I haven't thought about it, but I think they should not be isomorphic. So first let's try if we can find a counter example. I think converse should not be true. So suppose we take n equal to 4. If we take n equal to 4, then how many edges this graph will have? So we have 4, choose 2, which is 4 into 3 by 2, which is 6. So now we have that G and G bar should have 3 edges. So now can we construct a non-isomorphic graph? Two like basically we have 4 vertices, and can we construct non-isomorphic? I think we can. Just consider this. If we take this to be G, if we take this as G, what will be its complement? Its complement will be,
A number of edges should be 6, not 3, I think.
yeah, number of edges are 6 in the complete graph. But now,
Yes,
then in G it will have 6 by 2, right? G will have three edges, G bar will have three edges.
Yes.
Yes. So now if you look at this, if you take this as your G bar is this, right? But
Uh,
are they isomorphic?
but here the number of edges is not the multiple of 4.
Oh, we are not. The question is number of vertices should be multiple of number of vertices should be multiple of four. We showed
Oh,
that
yes,
n
yes, yes.
we
Yeah,
showed n
yeah. Right.
equal to 4, like number of
Yes.
vertices. So
Right,
say,
right.
so see, this is the counter. So, and you can easily see that these two graphs are not isomorphic. Can you give me a reason why they are not isomorphic?
Yeah, so we have one vertex of the degree 3 here in the G, and we do
Hmm.
not have
There
any
is no
such.
vertex of g bar, so
Yeah, yeah,
converse is not true.
yeah, yeah. Thanks, thanks.
It is a cycle, it is a tree.
Yes, yeah, that is also true, that it has a cycle but it has no cycles. So they are clearly non isomorphic, and we can give lot of reasons to say that they are non isomorphic. Even they don't have same degree sequence even. Yeah. Okay. So this was the question. So we have done this. Okay. Before this, let's introduce the diameter. Yeah. So now let's come to the last topic of today, which is diameter. So first of all, there are two notions. What DUV, this refers to the length of shortest path between U and V. And diameter G is maximum of all those shortest distances. So let's understand them with examples. So if I take Kn, say K3, K4, let's take K3 is too easy. Let's take K4. Uh, so can you say anything about D V1 V2 in K4? So DUV is basically length of shortest path between U and V. So what is the shortest length of the shortest path in the complete graphs?
1.
Yes, because all vertices are adjacent. So we see that dv1 v2 is 1. So what will be the diameter of kn?
1 again.
1. What about complete bipartite graph?
Length between two vertices can be 1 or 2,
Yes.
and diameter will be 2.
Yes. So did you understand? So if it is a complete bipartite graph, that means we have two partitions A and two partitions B. So if we have, suppose V1 and V2 are in different partitions, what is the length of shortest path?
2 in case of
Nahin, nahin.
bipartite.
If it is a complete bipartite graph, V1 is
One.
lying in A and V2 is lying in B. It will be 1 because there will be an edge
Yes,
here, right?
yes, yes, yes.
And what if there are two vertices in A? What is the length of shortest path between V1 and V3? 2.
0.
Two,
Right?
man.
No, no. Length of shortest path.
Okay, I
Two.
see. Yeah, 2.
2, because we can go to some vertex here and then here. So it is 2, because either the shortest length is 1 or 2, and what is the maximum of 2? 1 and 2 is 2. Now third is C2N. Suppose I have C4 first. A,
N
B,
will be there.
C, D. So what is the uh, shortest length of shortest path between A and C?
2.
Two.
And what is, and so we can see it is either 1 or 2, so therefore diameter of C4 is 2. What about C6? So C6 is this,
So
basically
this,
V1
yeah,
V2
this would be 3 then.
V5 V6. So What is
Diameter
yes?
diameter diameter is 3.
Diameter is 3. Why?
So if we go from V1 to V4,
Diameter
see,
of C6 is 3 because V1 and V4 are the farthest one, and there the length is 3. Sorry, there's some disturbance. Yeah. So is everyone convinced why diameter of C6 is 3?
Yes, ma'am.
So now
Yes,
can you generalize what will be the diameter of C2n?
That would be equals to n. We would be having two paths for the vertex, which has
Hmm.
got the largest distance.
Hmm. Hmm. Hmm.
So yeah,
Yes.
this would be equals to n.
Yes, we can. So diameter of C2n will be n. Now what about odd cycles? What is the diameter of C5 first?
it would be 3.
So does everyone think it's 3? See, look at the diagram.
Yeah, 2, 2.
Diameter of C5 is 2, right? Because C if you C1 and C4 can be connected by this shorter path of length 2. So diameter of C5 is 2. What about diameter of C7?
3.
So basically diameter of C2n plus 1 is also is coming out to be n, right? Because we can draw the cycle like this. Suppose we have v1 till vn here, and then we have vn plus 1 here, and then we have vn plus 2 till v2n plus 1. So there are n vertices here, and there are n vertices here, and one more vertex here. So this is the cycle. So v1 and vn plus 1 are the farthest one, and they have length n. Therefore diameter of odd cycle of length 2n plus 1 is n. So is everyone clear why diameter of C2n plus 1 is n? Okay. Now these were very simple examples. We'll do some questions on diameter. So first one is, if shortest distance between UV is greater than equal to 2, show that there exists at least one W such that du plus dWV is equal to duv. So I'll so first this is A part and this is B part. So first we are doing A part. So we are given that length of shortest path between U and V is 2. Is a greater than equal to 2. Suppose U is equal to V1, V2, Vk equal to V is the shortest path between U and V. So basically you have U here, you have V here, and we have some path V2, U is equal to V1, and we have some path here Vk minus 1 V. Now you have to what we have to show that there exists at least one W such that duw plus dwv is equal to duv. So can you find me one such vertex which is satisfying this inequality, this equality? So first of all, one thing is always true. Suppose suppose DUW is K, sorry, DUW is M, and DWV is N. So what can you say about DUV? Is there any? So there's a path
M
of,
M plus N.
no, no. D, so this is the shortest path between UW is of length M, and shortest path between WV is of length N. So we so the, so basically, wait, suppose this is the suppose this is in this C5 only. This equality need not be true always. Suppose in C5 we have this vertices V1, V2, V3, V4, V5. So so we have a so basically, uh, in this it will be true. Okay. uh, so this need not be true always, in the sense, like, see, if we have, suppose this is my graph, suppose this is my graph, yeah. So what is distance between, shortest distance between V1, V2? What is in this graph, what is dv1 v2?
One.
What is dv1 v3? Sorry,
One.
v2 v3.
One.
But what is dv1 v3?
DV1 one, but then in the question,
There's a,
medium distance is
sorry, there's,
Even it is
so there's, sorry, there was a disturbance, I didn't hear. Yeah, what is dv1 v3?
it is V DV1 V2 is 1 and V2 to V3 is 1, so it is 2.
No, dv1 v3 by definition is shortest path between v1 v3.
One.
1.
1.
Yes. So this is, so basically I'm saying this equality need not hold always. So in this case we are getting dv1 v2 plus dv2 v3 strictly greater than dv1 v3. So if duw is m and dwv is n, we cannot say that duv is m plus n. We can only say that duv will be less than equal to m plus n, because if duw is m, that means we have a path of length m between u and w, and there dwv gives a path of length n between w and v. So we get a path of length m plus n, but that path need not be a path of shortest length. Therefore, duv is less than equal to m plus 1 n. In this case, we see, so we are getting a path between v1 and v3 via v2, but it is not the shortest path. Okay, so now do you understand why do we need this question? So in this question, we are saying that, so we have always this inequality always hold, but this question is saying that we have to show that for one vertex this equality is also holding. So does everyone understand what the question is saying?
actually, this question is not clear. So,
So
to
yeah.
my understanding, this question says that if the minimum distance in between any two vertices is greater than or equals to
To
2, then
2.
definitely there would exist a common neighbor. That's it. So,
No, no, there, no, not a common neighbor.
there would exist a vertex.
uh,
So, a in between vertex, a W.
no, no, so I am just this is saying that if shortest path between d and uv is greater than equal to 2, it need not be 2, it can be greater than 2 also, then we have to show we can always find at least one vertex for which this inequality is holding.
Yes.
So I'm just saying that if yeah, even if there's a path between u and w and there's a path between w and v, then we can't say the resultant path that we are getting between u and v will be the shortest path. But this question is saying we can guarantee at least one vertex will be there which is satisfying this property.
Yes, but then the example you have taken,
What example you have
in
given?
this example, the minimum distance is not equals to at least two. It is already given as one here. So
Yes,
in the
yes.
counter
No,
example, yeah,
yes, yes. In this, no, no. So in this example, I was just saying that the so equality basically by the way of this exam. So somebody said that duw is m, dwv is n, then duv should be m plus n. So I was just showing that this need not be true.
okay, yeah,
Yeah. So I was just showing by this example, I was just showing that if duw is m, dwv is n, then it need not be true that duv will be m plus n.
yes, right, right.
Okay.
That is true. That is
That
true.
is,
But
yeah.
then it does not mean that there won't be any vertex
Yes, yes,
W.
yes. But so now you have to find such one vertex. Now
Yes,
we return back to our question.
yeah.
So now, I'll just erase this one because this was just an example. So now is the question clear to everyone? So is question clear to everyone?
This is a triangle inequality.
Kind of. Yes, yes. You can say.
Ma'am,
Yeah.
uh,
So
just
case
just wanted to confirm
W is
the
K.
approach of it.
Sorry,
Like,
sorry. I couldn't hear. Yeah, yeah.
I just wanted to know that one approach was coming in my mind. Like, will
Yes,
we
yes.
divide it in the sense of cyclic graphs and graphs which doesn't have a cycle?
No, not necessary. We don't need to go into cycles.
Okay, okay.
Okay, so let me give you a hint. So what about, let's look at this first vertex only. So what is dv1 v2? What is dv1 v2?
One.
1. And so this is a so this is a so suppose this is a so these are v1 k vertices. So this is a shortest path between u and v. I am assuming that duv is equal to k minus 1. So this is a path of length k minus 1. So what can we say about dv2v? What can we say about dv2v? So what this length, this path length, what is this length of path?
K minus 2.
K minus 2. So there is a path between v2 and v of length k minus 2. So we can say that dv2v will be less than equal to k minus 2. Right? Because dv2v is the length of the shortest path. And we have a path of length k minus 2. Therefore, we see that length of shortest path should be less than equal to k minus 2. So if the length of shortest path between v2 and v was k minus 2, then we would be done, right? Then v2 will be the resultant vertex, right? So, right, if dv2v dv2v is equal to k minus 2, take w to be v2, then we are able to, then we are done, because then we get that du v2 plus dv2v is equal to 1 plus k minus 2, which is k minus 1. So I am saying that yeah. Now tell me, so if dv2 v was k minus 2, we would be done. But can dv2v be less than k minus 2? Is it possible that we have a path of, we have some smaller path
No,
between
not
u and v?
possible. Not possible. Otherwise, the value of the shortest distance could have been less than k minus 1.
Yes. So if dv2 v is less than k minus 2, then we get a path from u to v2, and then from v2 to v. So this has length 1, and if this length is strictly less than k minus 2, we get a path of length less than k minus 1, which is a contradiction. So we see that, if we just take the adjacent vertex to v2, then this is satisfying this criteria. But if we were taking any other vertex in middle, then we couldn't say anything, because dv3 we know that there is a path of length 2 between v1 and v3, but we have no idea whether v1 and v3 are adjacent or not. So we don't know whether this is the shortest path between them.
So, but it could have been possible that there is no path, say, from V2 to V, and there exists a path from V3 to V rather. And then I'll have to make a move from V1 to V2 first, and then from V2 to V3, and then make a jump to V3 to V, say, by using k minus 3 number of the vertices. So, in that case, instead of a single W, I would be having more than one W here.
Haha. So yes, so the question says that there exists at least one W. We are not saying there exists exactly one W.
Oh, I see. Yeah, clearly.
So we are getting at least one W. So I'm just saying that this same argument need not work for V3. This is only working for V2. So now is everyone clear about this question? Any doubts in this question?
So why don't we prove it in the contrapositive way kind of the thing? Let us assume that for all possible W's, this is true, and then finally we negate thing, and then we can say that this would be possible if the shortest distance in between U and V is equals to 1 in that way. So can't we move forward in that direction to prove this statement?
I think that will be more complicated.
Okay, okay.
This is very simple, right?
Yeah.
In this, because v1 and v2 are adjacent, we can say that their shortest distance should be 1, because it cannot be less than 1. And then we can by v2 and v, so by v2 and v, and with this argument we are saying. So now b part is very similar. So now you have to give, if you have understood a, then b should be easier to you. So b part is saying, if duv is greater than equal to 3, then we can find at least two such vertices. We can find at least two such vertices. So suppose if, so basically if in this case it duv was just 2, clearly we cannot find two vertices. But now we are saying that duv is greater than equal to 3. That means we have u, v1, some vk, and v. Now can you give me two vertices which will satisfy this condition, that duw plus dwv is equal to duv? So first vertex is v1 only. We have already shown we can take w to be v1 from previous question, because if duv is greater than equal to 2, we have shown it, right? We can take w to be v1.
So now if we fix the value of the V1, that V1 is always there. So then the question reduced to getting the minimum distance in between say V1 and V is less greater than or equals to 2. will reduce to the first question only, and wherein we would definitely be getting a single W. So first W is fixed as V1, and the other W we'll get from the part A of this problem, and probably it is proved in that way.
So how are you getting the second thing from part A?
So second thing from the part A is now the question reduced to getting the minimum distance in between V1 and V is greater than or equals to 2. See, if the minimum distance in between U and V is greater than or equals to 3, and if we fix the value, if we fix V1 as the first vertex, right? So then we are left with getting the minimum distance in between V1 and V is greater than or equals to 2.
But then there's an issue.
Yeah.
So okay, so okay, you are basically saying we know that distance between, nahi, why it is so so okay, there's an issue. So you are saying you apply the first part to v1v.
Yes.
So suppose you are getting some w prime from that,
Yeah.
right? But then you have to say that du w prime. So from this you are getting that dv1 w prime plus dw prime d v
V, yeah.
is equal to
DV1B.
v1v. But but why you have to show du v is
Mhm.
equal to du w prime to show v. So how can you conclude this?
So to show that du comma v, I'll show that du comma v is equal to du comma v1, and then plus dv1
Ah,
comma
but
dv1
that
comma
need
v.
not be true. See, suppose you were getting this w1, so
Mhm.
you, but if there's, so I'll give you a counter example only. So this your argument won't work. Suppose this is the graph, okay?
Hmm.
Suppose this is the graph. uh, Basically we cannot like, okay, there's a uh, basically okay, I can't construct a counter example right now, but see, you have to say that then. So we are getting that dv1 w prime plus dw prime v is dv1 v.
Yes.
So now you will have to basically show that du of w prime is same as dv1 w prime plus 1, because we know du this is 1.
Yeah, so this is one because v1 we have already picked a vertex which is adjacent to u, and such an adjacent vertex will definitely exist. Otherwise, how would I construct a path?
uh, no, I'm saying, see, this, we know that we are getting this inequality, but why is this equality?
So this equality, because here say du comma v, I mean, it is not necessary that there should be. Okay, so you want to prove this inequality that
No, this
d of,
inequality is already there.
yeah.
But okay, we can try this, but I think this might not work. But see, we find an adjacent vertex to v1. What about vk? Oh, okay. Yes, what about vk?
But then I'm not interested in getting vk as such, because once I fix the value of the v1, my problem reduces to the part A of the question.
Yes,
And
yes.
according to the part A of the question, a not middle, but then definitely an inward being vertex w will definitely exist. So one w from there from the part A, and then one v1 which I fixed just now. It could be any adjacent vertex.
No, I understand it, but I think your argument is a bit incomplete in the sense that you have to show this equality also.
And what
So
does it
maybe,
indicate?
huh? No,
What does it?
this inequality is whole. Basically, see, you from this part you are getting this question, this one,
Yeah.
right?
So even I'm not sure, there could be a flaw in this argument, but yeah, even I do not know. But you can continue with the way you were proceeding earlier. It was just an idea. Yeah.
Yeah. So I'm just saying, so if we so basically if duv is greater than equal to 3, then we know that v1 is not equal to vk, because there is a path of at length at least 3. So v1 can't be adjacent to v, so we know v1 is not equal to vk. And we know, and like previously, now we can do this, that dvk v is 1 and duvk cannot be less than like it cannot be a smaller path so if it is a if duv is equal to k, then duvk cannot be a smaller path, because if it is if so basically from this we get that duvk is less than equal to k minus 1, but it cannot be strictly less than k minus 1, because it cannot be strictly less than k minus 1, because if it is strictly less than k minus 1, then we are getting a shorter path. So basically we have to repeat just the above part argument of part A to the vertex vk. The only difference is that if duv is greater than equal to 3, we can guarantee that v1 and vk are different. So now do you understand that? So basically, if duv is greater than equal to 3, the immediate vertex to u and immediate vertex to vk, the immediate vertex to v will satisfy this equality. So we are getting at least 2 such vertices. So is this argument clear? Okay. Okay. Now let's look at the last question. Okay, so this is the extra question. The first question is this. Uh, so this is we'll do this is the last question now. So G is a graph whose vertices are 2-element subset of 5-element set. Edges are pair of disjoint 2-element set. What is diameter G? So first we need that 5-element set. Let me call this 5-element set is 1, 2, 3, 4, 5. So read this question. So the vertices of these graphs are 2-element subsets. So what are the possible vertices of this graph? How many vertices will this G have? If my S is 1, 2, 3, 4, 5 and its vertices are basically all those set T such that order T is equal to 2. So all these subsets are my vertices. So how many vertices does this graph have? So did everyone? Yeah.
5C,
Sorry.
5
Uh,
Yes.
5p2, yeah. So,
5C2.
but 5p2 because order will matter here.
No, no.
So,
Order won't matter. 2, 3 is same as 3, 2.
okay, then
Right?
10. 10.
So order doesn't matter. So basically 5C2 vertices, which is 5, 10 basically. So now number of vertices are 10. So now can you say what will be the, suppose this is my V1, what will be the degree of V1? So we have that basically if we have 1, 2, so okay, sorry, I'm just saying, suppose my V1 is 1, 2. So what all vertices are adjacent to V1? So we have that edges are pair of disjoint 2-element set. So vertices are this. So vertices are basically 1, 2, 1, 3, 1, 4, 1, 5. We have 10 vertices, so I'm just listing them down. 2, 3, 2, 4, 2, 5, Then we have 3, 4, 3, 5, and 4, 5. So I have a list down 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are my 10 vertices. So now this is saying that we have an edge. So these two have an edge if they are disjoint. That means their intersection is empty. So basically what are possible edges of 1, 2? So what are the adjacent vertices to 1, 2? Their intersection should be empty. Disjoint means that their intersection should be empty. Will 1, 3 be adjacent to 1, 2?
No.
Okay. So what all possible adjacent vertices are there?
So no vertex, no element should be common. I
Yes,
mean,
disjoint means no their intersection should be empty.
so like in this case, we have one, two, three, four, five, six. We have
So
six
we cannot
possibilities.
have one or two. So we have to form two element subsets out of 3, 4, 5.
Yeah.
So basically it will be 3, 4, 3, 5, and 4, 5. Right?
So effectively, we are left with then three C2 number of the
Yes,
possibilities.
basically that. Yeah. 3C2. So you see that this is a regular graph of degree 3. We can do it for anyone, any. So I did it just for 1, 2. If I would have taken some other a, b, so we have to find disjoint element sets. So a, b, there are 5 elements, so how many elements are left? 3. And you have to make two elements, uh, two element subset out of these two, which is 3C2, which is 3. So it will be basically 3. So now did everyone understand what are the vertices and what are the edges? Then only we can compute the diameter.
So, can you explain one more time the question again?
Yes. So I'm just
Um,
so so we are so I'll say G is a graph whose vertices are two element subsets of 5 element sets. So basically my S is this 5 element set, and the vertices are two element subsets of this. So there are five elements, and I have to look at all the subsets of this set which has two elements. So this will give me 5C2 option, which is 10. So I will get that there are 10 vertices. So these are the all the vertices. Okay. Now we say there is an edge between two sets, two such sets if their intersection is empty. Okay. So if I pick 1, 2, it won't be, there is no edge between 1 2 and 1 3 because we have one common. Similarly, there is no edge between 1 2 and 1 4 because we have one common. So all the possible edges containing 1 2 will are only these, that is 1 2 will be connected to 3 4, 3 5, or 4 5. Now do you understand what is the, like,
yes, yes,
so
yes.
we have the vertices, we all have the edges. And if you'll try making this graph, you'll see that this will come out to be Peterson graph, because you can, like, I can so if you'll try drawing this, you can see that. But without drawing this graph also, you can compute the diameter. So we have to compute the diameter of this graph. So, so first tell me what is the distance between AB and CD. If basically these are distinct elements, ABCD belongs
One month.
ABCD belongs to 1 2 3 4 5, and they are distinct. So why the distance is 1?
These two sets are distinct.
because they are disjoint and therefore there is a edge between them. What if, what happens if they have one common element? What happen if they have one common element? So I'm basically saying that 1 2 and suppose 2 3. So there is no
There
edge
is no
between
edge
them.
between them.
There is
Yes.
no edge between them, so it cannot be 1. But can they have a common vertex? So suppose if they have a common, if they have a common vertex, then we can say it is 2. So if they have a common vertex, then we have to find a set AB which is disjoint from 1 2 as well as 2 3. So is there any two element set which is disjoint from both 1 2 and 2 3?
4, 5.
4 5. Yes. So we can just take AB equal to 4 5. So in this case also, if we have basically ABC, and there are, we can just take, so we see that if they have no element in common, then the shortest distance between them is 1. If they have one element in common, then the shortest distance between them is 2. So are there any other possibilities between the vertices? Because if we have two element subset, either they can have one element in common or no element in common, if they are two distinct sets. So
5 4 and 4 5 is same, ma'am.
yes, yes, 4 5 and 5 4 are same. So what now, what is the diameter then?
In this case, it is 2 then.
Yes, in this case it is 2, because either we have a distance, shortest distance is 1 or 2. So we see that diameter G is 2. Okay, so this was all for today. Do you have any doubts in the questions that are discussed today?
Lot, lot of theory. Thank you.
Okay, so if it is fine, then okay, so we'll end the session. Okay.
Thank you. Thank you.
Yeah, yeah,
Thank
Thank
you.
you.
yeah.
Thank you so much.
Yes.